the Vasicek model calibration. Okay, so before we begin calibration, let's first discuss what we were, what we know about the Vasicek model. Okay, so in the last lecture, we were discussing that the Vasicek model is an interest rate model, which models the short rate or the instantaneous spot rate. Okay, and why do we need something kind of a model which models the short rate? Because all other fundamental quantities, for example, if you have bonds, whether it is zero coupon bond or coupon bearing bond, or you have any other instruments, for example, other rates for any other maturity, that can be expressed as an expectation of the short rates, right? That's why we need a sort of a model which can model the short rate. So Basic model is models the short rate in the market. Okay. The other thing is that the underlying equation in the risk neutral measure, of course, is this one, as you can see on the screen, which is k theta minus rt dt plus sigma dwt. Okay, where rt is the short rate. Okay, and drt is a change in short rate in a time period called dt. Okay, so far so good. In the last lecture, we were discussing calibration, right? What calibration is. So basically, calibration is nothing but to find out what is the value of appropriate parameters, like what will be the value of k, theta, and sigma, right? So now we have two equations. For example, the equation under the risk neutral measure or the equation under the real world measure, right? And as we already know that the original Vasicek model was written in which measure? What was the original measure in the equation in the Vasicek model, basically?
The risk neutral
P
measure.
value, P measure.
It was the real world measure, right? As per our discussion in the last class. So I recommend you once read the original paper as well. It will be quite interesting. So the original measure in which the model was written was the real world measure. But here we are calibrating in the risk neutral measure. Okay. So let us just discuss briefly. I will take around 1 or 2 minutes and then we would start today's discussion. Okay. We were discussing that when you calibrate something why do we calibrate first? To find out the parameters. Okay. Now, when you calibrate something to the market prices, what does it mean? You are finding a set of optimum parameters, okay, such that the prices given for those instruments by the model is as close to price that is in the market, okay. So we are interested in that set of parameters for any particular model that will give you prices which are as close as possible to the market observed prices, right? Now, when you are calibrating something to the market observed prices, what are market observed prices? They are the risk neutral expectation of the people, right? So that's why those prices are the risk neutral expectations only. That's why when you calibrate something to the market observed prices, current market observed prices, you use the risk neutral measure. Okay. Now, when you are using any historical data, for example, historical data of the short rates, right? For example, what was the short rate on first Feb, second Feb, third Feb, fourth Feb, and all, then you will be using a real world measure because you are taking the data from the real world. Okay. But please remember that when you are using those data, the data of the short rates, right? Historical data of the short rates, those are quite different from using the historical zero coupon bond data. Because in the risk neutral measure, when you are using the zero coupon bond data, for example, let us say at this moment, there will be 50 zero coupon bond, let us say, of different maturities. So those prices of the zero coupon bonds are at this instant. All the 50 prices are of this instant only. Okay, got it. But when you are taking historical data, they are, for example, some data is taken from first Feb, some data is taken from second Feb, third Feb, fourth Feb, fifth Feb, sixth Feb, right? So this is nothing but taking the data from the real world. So that's why you will be using the real world measure to calibrate to the historical prices, right? To historical data basically. But you can't take the past zero coupon bond data. Why? Because you can't take historical data so you can't take a historical series of the zero coupon bond data, right? You can take the data from only one instant, right? For example, you can't take the price of a zero coupon bond of a maturity, let us say 20 years from first Feb, and the price of a zero coupon bond of maturity 50 years from second Feb, right? So you can't do this. So all the data need to be taken from the same instant only in case of a zero coupon bond if you want to have, right? And otherwise it would be too inconsistent. That's why When that's why in the real world measure, when you are calibrating, it is better to calibrate using the historical sort rate. What does it mean? uh, what was the sort rate on first fab, second fab, third fab, fourth fab, and then you can use a maximum likelihood estimation or other techniques to find out the set of parameters that will give you this sequence of sort rates, right? Under the real world measure. Okay, so now let's get back to the risk neutral measure. As I already said, uh, we have the historical prices of the zero coupon bond. Sorry, we have the current prices of the zero coupon bond, and since this is the current price, this is the risk neutral expectation of the market basically. That's why we'll be using the risk neutral measure to calibrate to the zero coupon bond prices. We'll be finding a set of k, theta, and sigma, which gives the price as close to the market observed prices of the zero coupon bond. I have already sent you the data of the zero coupon bond. Please download it and save it in your system. Open Google Colab, and on the on the left side, you see this option. Therein you can upload basically the file over here. Okay, so basically, I have uploaded this data. I have also sent the JetCB price data on your to you. Just download it and upload it into Google Colab or any other system that you any other ID that you are using. Okay. So before basically starting the calibration, let us just simulate our model. Okay, let us just simulate the Vasicek model using any set of arbitrary data. For example, let us assume k equal to 2, theta is equal to 0.05, r naught is equal to 0.03, sigma is equal to 0.02, and dt is equal to 1 by 365. Okay, dt is in years. Okay, so basically we mean dt is equal to 1 day for us right now, right? But it is converted in year. Okay, so we are having a list which is r, right? So it will store all the sort rates that will be given by the model. The first sort rate is already added into the list, which is R naught, which is the current sort rate, which is 0.03. That means 3%, right? Okay. So now we'll be simulating it for 1 year. That means first day, second day, third day. So basically 365 days, right? Now, as we already know, dRt is equal to k into theta RT plus d sigma dWt. So basically, it is dRt, right? So once you know RT, so once you know R naught, you can calculate R1, right? How can you calculate R1? You can calculate R1 by adding R naught plus dRt, right? So basically, what I mean to say is, text. So basically, R1 will be nothing but R naught plus dr, right? Now, once you calculate R1, what will be R2? R2 will be uh, R1 plus dr, but note that this dr and this dr will be different. They will be calculated because every time you calculate dr from sigma dwt, this will be giving you different values, right? So that's what we are doing over here. This is the current sort rate r minus 1. So basically you are taking the last entries of this list, right? And then k into theta minus r minus 1, which is the current sort rate, into dt plus sigma. Now dwt is nothing but a Brownian motion, right, of mean 0 and a variance of dt. Okay, so it is nothing but equal to root under dt into a normal distribution of mean 0 and a variance of 1. So that's what we have done, right? And then once you get the next sort rate, just append it into the list, right? So we are appending r1 over here, r1 in the list. Okay, and again, so once you do, so for example, in the first iteration, you will get R1, and then again, uh, your R will be containing R naught and R1, right? And then, so let us just write it as R because it will be more, it will make more sense, right? So once you do the first iteration, you will have R1, which you have appended into the list. So now list contain two rates, R naught and R1. Again, using the R1, so basically R minus 1 will be R1, right? This take the last entry of the list. So R minus 1 would be R1 only. So then you will get R2. Then you will be appending into the list. So this way you get around 365 sort rates. That means what will be the sort rate on this day, sort rate tomorrow, sort rate day after tomorrow, sort rate what will be the sort rate till after till 365 days, right? So basically if you print your R, right? Print R, right? You will have your sort rate. Just a minute. Okay, so there, because we have already defined R in the bottom, so it will make an issue, create an issue over here. So
R of 5 maybe, if you could.
Yeah, just a minute. Tell. So let us write this list as rates because we have already defined R in the bottom. So that's why it will create an issue.
No, no, keep that as R because then you have to change a lot of R's.
No, we have not used in the bottom. So that will not be an issue. So it is a separate list. Okay, so you get a list, right? So this list contains the rates, sort rate R, right? So basically all the sort rates. You see, this is the first sort rate. Basically, it starts from 0.46, 0.046, 5623. This is the sort rate on the first day, and so on, right? Any issue? No? So now let us plot it. So this is the plot that you get, okay? So you can try changing different parameters for K, theta, R naught, sigma, and dt, and eventually you will be getting different. Uh, Basically, every time you run this iteration, you will be getting a different curve because of obviously the normal term, because of the random terms that is there, right? Any issue? Any question on this front? If you have any question, just let me know. Okay, so it's time we start the calibration. Okay, so just upload the data so in using this technique. So basically, if you're using Colab, then you can just copy the path from here. Just use copy path and then panda.read CSV and then put it inside, and then you can just get your data. Okay, so if you get the data, I will just use print data, and so this is our data. Okay, if you see over here. So this is the maturity. Okay, these are the rates and these are the ZCB prices, the zero coupon bond prices. Okay, please note that these prices is out of 1,000. Okay, so it means the face value of the bond is 1,000 and this is the ZCB price. Again, these are the rates, but again, these are the rates, but in percentage. Okay, these are the rates, but in percentage. So whenever you use the rates, just divide it by 100. Okay, so that it is in decimal points. These are the maturities. That means I think this is around 1 day or 7 day, I guess. Okay. For example, this is 1 year, 1.5 year, 2 year. So all these maturities are in years. Okay. Any doubt?
So last maturity 27 means 26. Sorry.
50 years. Last maturity is 50 years. Okay.
Okay.
So now we are calibrating to the market prices of the zero coupon bond. As we already know, in using under the Vasicek model, in the risk neutral measure, the formula for the zero coupon bond prices is this: A into e to the power minus b into r. Okay. We have the current zero coupon bond prices. That means the zero coupon bond prices right now. That means t is will be zero, right? This t will be zero, small t. This capital T stands for the maturity. So we already have the maturities of all the zero coupon bonds. Okay. And what is A and B? The expression for A and B are given. You see that to find out A and B, you will be needing the parameters K, theta, and sigma, right? So that's what we have to do. Okay. So R naught is already there, but we, as of now, to increase the number of parameters, we'll be assuming R naught also as a parameter. Okay, but let us take, so this doesn't count. So basically, even if you don't do this, it will be okay. So let us ignore this part. Okay, now what is parameters? Parameters are basically the list of how many parameters are you having. So we are having 4 parameters: the K, sigma, theta, and RT. Okay. So basically we are storing it in a list. So the first element of list corresponds to kappa, which is K, the mean reversion speed. Sigma is again the volatility. Theta is nothing but the mean reversion level. And this RT is nothing but at what time are you calculating the zero coupon bond prices. But since we are calculating it right now, so that's why RT will be nothing but R naught. Okay. Because small t is zero. Okay. Now let us store the model prices in a list and again the market price in a list. Okay. That's what we are doing. Now we'll be iterating through this data. Okay. Please note that all these prices are the market observed prices. Now, given this formula and given a small t is equal to 0, right? And we'll be trying different values for the and maturities we already know, okay, right? Maturities are there for the so we have around 28 zero coupon bonds, okay? For all the zero coupon bonds, we have the maturities, right? Their maturities, okay? And apart from the maturities, we required a small t, which we already know, which is 0. And apart from that, to calculate their prices of the 28 zero coupon bond that we have, we need k, theta, and sigma. Okay, we'll be trying different value of k, theta, and sigma, and that k, theta, and sigma will k, theta, sigma will be corresponding to the to the model parameter, right? Which will give you the zero coupon bond prices as close to the market observed prices, right? So let us do it. So basically for index and row in data rotator, so basically it is a way to iterate through the data. So basically what we'll be doing, market prices, right? So market prices you already know. So in each row, basically go through each row and their ZCB price is the market price, right? This is the market price. So we'll be appending it to the market price list, right? Now for this Z0 coupon bond, its price we have already included, appended it to the list. Which list? Market price list. What is its maturity? This one is its maturity, right? So this is capital T. So this corresponds to capital T, which is the maturity. Now we can easily find, so we will pass some parameters, which is k, kappa, sigma, theta, and rt, right? Rt is nothing but r naught. So we'll pass these four parameters, right? And we already know what is B, formula for B, A, and finally the formula for P, which is the zero coupon bond price. Okay, this is the zero coupon bond price as predicted by the model. Okay, so we'll be appending it to the list. Which list? Model price list, right? And then we are multiplying it by 1000 because this prices that you are getting is you are getting it out of one. So it is just by assuming that uh, so when you use this formula, this will give you price around 0.996, 0.998. So we have to multiply it by 1000 because our principal is 1000 in this case. But this formula was made considering the principal is 1. That's why we will just multiply it by 1000 and we'll be appending it to the model. So for all the zero coupon bonds, we'll be finding their market. So we'll finding their model prices and then we'll be appending it to the model price list. Okay. Anything? Any questions so far?
Till this point, we are just doing for zero maturity, right?
No, I
Zero
didn't understand. What are you saying?
are at zero. Now we are calibrating uh, the model price and this thing. We are just taking it for that as of time zero, right? R is
Yeah. So t, a
yeah,
small t equal to 0 means we are taking the current prices of the zero coupon
current
bond.
price.
That is a small t equal
Right,
to 0. So
right, right. Okay.
uh, for example, let us say so let us say you are in the history, okay? So you are doing this calculation on 13th of Jan, and let us say you are doing this calculation on 13th of Jan, and so obviously on 30, if you are doing the calculation on 13th of Jan, what will be the small t? Or the basically on 13th of Jan, the small t will be 0. Now you are doing calculation today. That's why t will be 0 because you are finding this price at this because the data that you have taken, small t, you are taking from right now, right? So that's why small t equal to 0 because you are using the current zero coupon bond prices, right?
Yes, yes, sir.
Okay.
Understood.
Now, once we have the model price and we have the market price, what we will be doing, we have to return the loss. What does the loss mean? It is not a loss, kind of an error, right? What does an error mean? We will be, so for the first zero coupon bond, what is the market price? What is the model price? Just uh, take the difference and square them. Do it for the all other zero coupon bond prices. Take their difference and find their square and sum all the squares. What am I saying is, let us just a minute, sorry. So take the first zero coupon bond, find their market price, right? So you don't need to find their market price. It is already there. find their model price taking any value of parameter. Okay, so this is for the first zero coupon bond. So just difference it, take their difference and square it. Okay, do it for all other zero coupon bonds and find their sums, right? So what you get is an sum of a squared error, right? So that's what I have already written. And then take, if you want to take their mean, that is also okay. If you don't want to take its mean, it's also okay. So it's on you whether you want to. So this is kind of an error, right? So you want to minimize this error. You want to minimize this error, right? Why have I included a regularization term? Basically, this regularization term is kind of there to basically, to penalize it. Why do we want to penalize? Can anyone answer this question? So basically, we are penalizing so this is the mean squared error. What is mean squared error? The sum of a squared error divided by the number of observations that you have, which is 28. So this is the error. So you want to minimize this error. So you can also pass it, right? You don't need to add the regularization term. Okay, that's also okay. So if you want to, so let us just don't do it right now. So what I will be doing, I will just be returning the mean squared error, right? Now, what you have to do, you need to optimize. You need to use a method which will be passing different value of these parameters, these four parameters, and then they will be returning you the loss function. Okay. So, for example, first time you passed certain set of parameter, you got certain error. Then you are doing it consecutively, right? Till you find out a set of parameter which gives you the minimum error, right? So this method is called optimization. Okay. So here we are using the technique of optimization of technique of a global optimization, which is differential evolution. Okay, so differential evolution basically finds helps you to find out a set of parameters. Okay, which gives you the minimum value of the error, right? So that's what we are doing. So basically, first you need to define a set of parameters. So basically, give you a sample value, but it is not needed in case of so these parameters are not needed in case of differential evaluation techniques, right? Okay, but still, because it will pass the parameters by themselves. Okay, so this is the parameters. Okay, I am just giving a bound for kappa, sigma, theta, and basically RT, but it is also not needed in case of differential evaluation. But in case you want to, you can pass out a bound that you think that your basically this is for kappa, this is for theta. Sorry, this is for kappa, this is for sigma, this is for theta. Theta basically means the mean reversion level, and this is for R naught. So basically, see, I have passed R naught from 0 to 1. That means 0 to 100%. So technically it is not a bound, right? But still, if you want to pass out, you can. Otherwise, you can safely remove the bounds. Okay. So and obviously you have to give. So differential equation takes minimization function. Obviously, the function that you want to minimize. So we have already written the different minimization function, right? So this is our minimization function. This is the function whose output I want to minimize, right? Which what is the output? The output is mean square error, which I want to minimize. Okay. So and this gives, so basically this returns a result, right? If you see the result, if you see the result, what does result, what does it return? What does differential evaluation return? Differential evaluation is a minimization technique. Okay, it is running. So this kind of error will be there because of the small number of because the small values of parameter that we are doing. We have to ignore it. Otherwise, if you want to encounter it, you can. So see, optimization is terminated successfully, and so these are all the data related to the optimization. See, almost all the optimization techniques that you will be using, whether it is local optimization or global optimization in Python. For example, in case of local optimization, there are various techniques, right? For example, BFGH method and all other techniques that you can use, right? SLSQP is there, right? Sequential quadratic programming technique and other obviously optimization techniques that minimizes a function, right? So basically here I have used the differential evolution. You can use any other optimization techniques that you want to. So basically they stop their iteration once they see that they are not able to improve the error. Okay, so basically they try different value for parameters which are k, theta, and sigma, and basically kappa it was sigma, it is theta, and it is r naught in the sequence that you have provided, right? So I have already provided it in this sequence. So basically the first sequence, the first uh, member is kappa, the second member of the list is sigma and all. So this is the result, and you can see the error. sum of a square error is like 13.04. Okay, so it is not able to minimize the function. So it is not able to minimize the loss below that term. Okay, so basically error below 13. Okay, and these are the parameter values for x. Okay, but this is very small number. Why? Because this is sum of a squared error, right? And the numbers that you are minimizing were in so basically you can see that it is you are doing something like 999 minus 996 square, something kind of that thing. So basically and basically sum of all those 28 terms, right? So in that sense the error will be quite a small, as you will be seeing. So and this x, so basically this result is kind of a list. Okay, so the x or dictionary, sorry, this is a dictionary. And so if you see the x part of it, right, it is the updated parameters, right? So you get what is the updated parameters. Okay, so if you see the updated parameter, okay, so this is your updated parameters, right? Kappa, sigma, theta, and r naught. Okay, now you can use these updated parameters, right, to find out. Please note that these values might be market inconsistent, but we need to look into it in case it is market inconsistent. But as of now, let us just focus on calibration because the data we might have got might be inaccurate and all, but still, yeah. So we'll be seeing how accurate our calibration is, right? So let us see. Okay, so we are again using these parameters. So basically now you have the parameters value, right? Kappa, sigma, theta, and r naught, right? Now, if you have the values of these parameters, update, calibrated value, so you have calibrated these to the market prices. So now the data that you have got is the market calibrated parameters, right? So now you can again put these market calibrated parameters and try to find out what will be the zero coupon bond prices of the zero coupon bonds that you were using according to the calibrated parameters. So here you see that I have passed the, so here you see I have passed the param updated, so updated parameters to find out the model prices of those zero coupon bond, right? With all the zero. So if you see the data, so you see this is the ZCB price according to the market, and this is the price according to the model, right? This is the ZCB price according to the market. This is the ZCB price according to the model. Now to find out the ZCB price, what is the parameters value it is using? These parameters value kappa, sigma, theta, and rho. Okay, sorry, not rho, r naught. So now if you plot it, if you plot this data, what you see is that they are exactly coinciding. Okay, that means the prices, so your model, the model that we have built, this Vasicek model, it is able to calibrate to the initial yield curve. So basically you had passed an initial yield curve, right? Initial zero coupon bond prices, and it is able to fit exactly, not exactly, but if you see there is a difference in this lower segment, basically for higher maturity zero coupon bond. So this is the market price and these are the model price, right? Again, this is 274, but this is 271. So this is not able to fit exactly, quite accurately. But if you see in basically macroscopic sense, then this is the basically result of our calibration. The initial yield curve. So this is not an yield curve because this is the prices. These are the prices of zero coupon bond. But still, if you so the basically the ZCB prices are denoted by this color, and the green color is the model prices, right? But if you see uh, on a macroscopic scale, the prices are quietly quite closer, right? Of course, we need to use more sophisticated optimization techniques and other approaches to calibrate exactly to the model, right? We have to take holidays into account and other day count conventions so that our uh, you know curve is quite close, right? For example, here you see the model price is 422 and the market price is 417. No, but still we are able to predict it quite closely, right? So this is the initial curve, yield curve. But as I had already discussed in the last lecture, that in the Vasicek model, the initial yield curve, since it is not taken as an input, we are just forcing using the calibration. We are just forcing it. So that's why there is. it is not able to reproduce the initial yield curve completely, but still it's a great result, I think, right? And you can use the initial, so you can use the updated parameters to, so basically, just a minute. Okay, so it is our, so you can use the updated parameters to simulate it again, because initially we are simulating using an arbitrary set of parameters, right? So now you can use the, you can replace R1 with R rates, right? Again, sorry, let it be R1. Let us just replace the list by R rates. Okay, sort rates. Any questions so far?